Alrighty, guys. Good morning and welcome back today to Algebra 1. Today is, I think, Wednesday, the 19th for you guys. As you can see that you got a sub today. I am out. I am not feeling great. I came down with something on like Monday afternoon that has not quite left me yet. So figured I'd avoid getting everyone else sick and taking people down with me and record a video lesson for you guys while I'm here at home to kind of keep the momentum going and launch us into the next part of what we're going to see for Unit 4, where we're going to sort of officially switch over from working with equations and we're going to start working with things called inequalities. You guys completed a summative for the first part of Unit 4 when I was there with you guys on Monday. My hope is that I'll be back in the classroom on Friday with those graded so you can see how you did, get some feedback, and then from there, as necessary, start working through some retake opportunities. But in the meantime, I want to make sure that we don't fall behind and we carry off where we left off with inequalities, kind of lead ourselves into the next part of the notes here for 4.4. As we get situated for our lesson today, please make sure that you are bringing your phone up and turning it into the correct numbered phone slot in the caddy over there by the teacher's desk. The sub knows that you guys have these assigned slots and that phones should be placed in them. So please make sure to take a moment and get that done as you guys are getting filtered in for today. Now, for our warm-ups, I want to go over, say, one thing from the old stuff on our Ready, Set, Go for 4.3 on page 27. Then on the next one, I want to maybe talk about our jumpstart. That's going to lead us into the conversation for the notes today, talking a bit more with inequalities. Here in Ready, Set, Go 4.3, we are working with inequalities and we're just kind of getting our feet wet, right? We're working to see if by doing things to both sides of them, we have a result that still comes out true, or maybe it's a little bit different, right? We want to think about like what's going on and why that might be happening. Now, we're going to keep revolving around kind of this original inequality that -9 is less than 2. One way that we've been sort of seeing with our partnered practice, after you guys finish the summative, to represent inequalities is with like the real number line, right? If I think about -9, which is much further to the left on the number line of 0 than, say, +2, which is just a little to the right of the real number line on 0, we know that -9 is less than 2 because -9 is further to the left, and that's now officially a true statement, right? So we start with an inequality in this context that is true. What I want you to do is maybe take a look at these four selected operations on the original -9 less than 2. What happens if you subtract 7 from both sides, or you add 15 to both sides, or you multiply both sides by 10, or you divide both sides by -6? Do you still have something that's true, or is it false? So take a moment here, maybe about like 2 or 3 minutes, and do these real quick. Try and see what you get as far as the truth value of the initial setup. All right, so as we go, and we take a look at some old stuff from our previous homework, this first thing is asking us to take the original inequality, -9 is less than 2, and subtract 7 from both sides of the inequality. So from -9, I'm going to lose 7. From 2, I'm going to lose 7. And what I get out of that is a new inequality that says like -16 is less than -5. And what I'm interested in checking is whether that's really true or if it's false. If I think about what's happening on a number line, I've got, say, -9 shifting 7 units to the left to become -16. I have +2 shifting 7 units to the left to become -5. Now, if I think about the numbers -16 and -5, is -16 further to the left on the number line than -5? Is it less than? We'll notice here that that is still a true statement. So that's true. There's no problem with that inequality. When I subtract 7 from both sides, I get the same truth value, right? The initial observation still holds. Now, I can do the same thing with, say, like adding 15 to both sides. So if I've got like -9 less than 2, and I add 15, what I'm thinking about on the real number line is taking each of these dots and moving them 15 units off to the right-hand side. So if initially I had a value that was at, say, -9, and I add 15 to it, what I'm now thinking about is, okay, that guy is now over here, something I think like +6. And if I had a number that was at 2 and I add 9 or 15 to him, he's way over here now at something like positive 17. So I've got 6 less than 17 in the inequality, and what I'm trying to think about is whether that's true or false. And I'll see here that that is also a true statement. 6 is further to the left on the number line than 17, so there's no issue there, right? Everything's coming out the way that it should when I do like addition and subtraction. Now, I also probably want to check this out with multiplication and division. If I think about multiplying both sides of my problem by 10, I've got negative 9 is less than negative 2, but now I'm going to multiply each of these by 10 and see what I get. And what I'll notice here is that I get an inequality that's like negative 90 is less than negative 20. So these numbers are going like 10 times further to the left than they initially were. I think that's like positive 2 there. Whoops. There we go. So my negative 9 is now 10 times further to the left than it was. My answer for 2 is now 10 times further to the right than it was initially. And what I'm asking myself here is this still true? And I'll see that it works, right? Negative 90 is less than positive 20. And then on our last one, we're kind of doing something similar, right? Instead of maybe multiplying, we're thinking like, let's divide. And what we got here is division on both sides by negative 6. So I've got negative 9 less than positive 2. I'm going to divide both sides by negative 6, and I want to see what I get here, right? Now, you'll notice these are going to turn into some fractions. 9 divided by 6 is like 3 halves. A negative divided by a negative switches to being positive. 2 divided by negative 6, that's going to be a negative number. 2 goes into 6 3 times, but into itself once. That's like negative a third. And what I want to ask myself is a positive number less than a negative number? That doesn't seem to be right. So something broke here, right? When I divided by a negative number, I'm going to see something a little different than what I ought to get. If I think about 3 halves as like the decimal 1.5, and I think about negative 1/3 as like negative 0.33 repeating, I see that it should be the other way around here, right? So instead of less than, I should really switch this to be greater than now in order to maintain the truth value of the inequality. That's going to happen from time to time when you're dividing or multiplying by negative numbers. There's another example here in the Ready, Set, Go. We're going to multiply both sides by a negative number, and you're going to see the same problem pop out of this. So with inequalities, what you might have started to notice, especially with some of our old material, is that when you add or subtract constants to the other sides, you don't really have to worry about anything. The truth value is the same, so you're just kind of focusing on the numerical operations, right? It's a little different with multiplication and division. If you multiply or divide by a negative number, you're going to notice something's kind of off. And our goal today is to kind of build on that and reinforce it and keep track of those potential problems as we move along from there. Now, for our retrieval today, I have for you guys 4 different representations of a sort of inequality. Some of these are kind of odd. Some of these may be not so intuitive as to what's really going on. But what I want you to think about here is for these 4 different representations of inequalities, which one of these doesn't belong? Every single one of these is the result of like taking a number and adding an unknown onto it. But which one would you say is not like the others? We'll kind of take a minute here and go from there. All right. So all 4 of these are representations in some fashion of taking a number and adding something onto it to get something different, right? That's a pretty vague description of the scenario that we're working in, right? It took me a while to kind of understand where they wanted us to go with this particular problem. But the thing that helped me was to look at part B here first. Part B, I've got like x plus 4. That's an algebraic expression. So it's telling me that I've got some unknown quantity that I'm adding 4 to see what I get, right? Now, if you think about B and C and how these things might be connecting, you could say that the gray rectangle represents the unknown quantity, right? But then you've got these 4 blocks that are added onto it to get this new expression x plus 4. So B and C are kind of related there in the sense that even though we don't know what X is, we can create this new quantity by adding these little unit blocks on the side and kind of going from there. Now, if you look at part A, what I'm going to notice is that this dot is on -5. And then the arrow is telling me that I'm going until about like -1 here on the real number line. And if I go down to part D, what you'll notice is I've got like -5 shifting to -1, and then -1 shifting to +3, and 3 shifting over here to +7. So it's kind of like I'm adding 4 3 times in a row, right? So you may have noticed that B was like the only algebraic expression of the lot, and maybe that thing is what makes it different. If you look at A and D, we've got real number lines that are representing this like unknown +4 that's happening. So part C is kind of different, right? In the sense that it's not like a number line diagram, it's more like a pictogram. D is different in the sense that you're adding 4 to something, but you're doing it 3 times in a row instead of just once, right? So, like a lot of these, what you're probably noticing is that some of these are the same and different in different fashions. I would say for me, if I was kind of unpacking this, where my opinion would go is that D is very much different in the sense that I'm starting with something and I'm adding 4 to shift around on the number line, but I'm not just doing it once, right? Unlike A, I'm doing it 3 times in a row, which is very different than what I see with also parts B and C. So usually there's not just like one correct answer here. I would say here there might very much be like a singular answer that D is very different. But that justification process of thinking through why, that's kind of the most important part for today, right? Instead of all of us kind of converging on the final answer, it's just more important to get the gears turning. Now, as we get rolling into the last part of what we're going to have for some of our material, we tackled the first part of our summative, and we're going to have part two coming up, not on the 17th or the 18th. I've got a typo here. It's going to be a little bit later, going into December. As we go, we are rapidly approaching the end of the year. So for those of you guys that are requesting retakes in the testing center for your summatives for Unit 3, you want to make sure that you get those done and turned back into me by December the 5th. Beyond that date, we're going to be very much up to our eyebrows trying to figure out the Unit 4 material and the final exam. So that's when we're going to close those submissions out. If you're requesting a retake because you did 75% or better, and you still want to try again and do even better than that, that's fine. But you got to make sure to request it in time and complete it before the 5th of December. Other than that, for those of you guys that are working through Raptor 101 and Raptor Academy, don't rush yourselves. Follow the procedure, take your time with it. We're going to take the second half of the Unit 4 summative on December the 4th or the 5th after Thanksgiving break. So what we're going to do is start moving through the second half of our lesson materials. We're going to maybe take a CFA before the break or after the break, depending on whether you're an A-day student or a B-day student. We're also going to sort of unpack everything with a day before the summative on our review, just to make sure that we got all of our bases covered, especially with that distinction between equations and inequalities. We want to make sure to kind of slow down there as we approach the beginning and the end. For our time in class today, we are switching over to inequalities, and we're going to start kind of small. We're going to think about like truth and what inequalities are representing and whether the truth value of those inequalities is going to stay the same when I'm performing operations on them, kind of like what we saw in our warm-up for some of our old Ready, Set, Go problems. Where we've been so far in Unit 4 is that when there's an equation between two sides of an equality, when there's an equation between two mathematical expressions, there's kind of a process, right, of inverse operations that we can perform on them to undo these things and eventually solve them out. Eventually, we want to get to the same process when it's no longer an equal sign, when it's like greater than or less than or equal or greater than or equal. But to sort of build up to that, we want to explore like what those properties were with equations and whether they still hold with an inequality. Now, what we've seen so far with solving is that there's these sort of algebraic properties that pop up all the time in the process, right? Sometimes if you have like a quantity B plus C and you multiply an A onto it, you can think of it as like a distributive property where you multiply it onto both of them. But we've also seen like the addition subtraction property of equality as well as the multiplication division property. In order to maintain the equality, if say you add a constant to both sides of the equation, that's fair game. But it's the same thing if you subtract a constant from both sides. versus, say, if you multiply a constant onto both sides or divide a constant on both sides. What we're seeing here with these properties is that if you do it to both sides of the equation, you're preserving the equality, you're preserving the structure of the problem, and they're really one and the same thing. So it's a valid move, so long as you do it to both sides. We also saw that in order to undo something, you got to think about what its inverse operation is. So if I'm like adding something onto an equation, we saw to undo that, we got to subtract something. And vice versa. If I'm subtracting something, I've got to add something. The reason that those are the opposites is that when you add or subtract them together, you get nothing. And we call that the additive identity. So the additive inverse is whatever you need there in order to add it onto the original to get nothing out of it. It's similar but a little different from multiplication. If you multiply something onto a variable and you want to undo it, you got to do division, which is the same thing as multiplying by like 1 over a. You can kind of think of it that way there. When you cancel out multiplication, though, you don't leave behind 0, you leave behind a 1. That's what we call a multiplicative identity because 1 times anything is just that thing. It doesn't do anything, right? Now, as we go into inequalities, we want to sort of investigate and explore about whether these properties are still true, or maybe they're potentially a little bit different. So where we're going to start the process here on page 31 is with a given statement, right? So in this particular instance, let's say that we have the statement that's like x equals 8. What we're going to do is take the original statement and do something to it. And we're going to ask ourselves, hey, in these two new things that I'm working with, which is greater? Now, if x equals 8, I'm now trying to determine whether x plus 5 or 3 times x plus 2 is greater. So I want you to pause the video here, maybe mull it over with your table partner. Which of those two things is greater? Is it x plus 5 or is it 3x plus 2? We'll sort of take it and go from there. All right. So to kind of launch this activity, right, we're thinking through like what the task is and we're trying to interpret like what's going on. We started with this original statement that x is 8. We want to know which one's larger, x plus 5 or 3 times x plus 2. What you're going to notice here is that 3 times x plus 2 is the greater expression. 3 times x plus 2 is greater than x plus 5 because if x is equal to 8, that means 3 times x plus 2 is like 26, right? 8 times 3 is 24 plus 2 is 26. Versus x plus 5, that's 13 because 8 plus 5 is 13. So if I put all that together, right, the result of 26 is greater than the result of 13. I can kind of show that with like a number line analysis if necessary, but we'll see here that 3x plus 2 is the greater expression. We're going to do the same thing with, say, this statement, right? That n is an integer number. And then we're trying to ask ourselves, which is greater? Is n greater or negative n? I want you to maybe think about this one too. If n is an integer, so like a whole number with a positive or a negative out in front of it, which one's greater, n or negative n? All right, so with this one, you may notice kind of like an interesting conundrum that pops up here about like the origin of our number, right? Here what they say is that n is an integer. So it could be a positive number, it could be a negative number, it could be 0, but it's going to be some positive or negative whole number, like -3 or -2 or 0 or 5 or 8. Could be any one of those things, right? Depending on what you imagine n to be, though, you might not get the same answer as somebody else in the classroom. If you say that n is positive, so it's like +3 or +5 or +8, you'll notice that it's off to the right on the number line, further off than 0. Which means then that negative n, the negative version of that, is off to the left of it, which would mean that if n is positive, n is greater than negative n. That's a true statement, right? But you may also have thought about this a different way. If you say that n is negative, like -3, for example, then the negative version of that thing would be like +3, and it would be greater than the negative thing. So if you choose n as negative, right, then negative n would be less than the positive version of it. Maybe you thought to yourselves, well, then negative n turns out to be greater than n, right? So there's kind of like a weird situation at play here, right? Where you might get two different answers in this context depending on how you're envisioning the original statement. And that's actually very much by design, right? You'll notice that as you go forward into the explore phase, that some of these expressions are very much set up in a way to kind of lead us down this rabbit hole, right? Where it's like, well, what do you mean? Like, how are we starting? And what we're doing here when we consider all these different possibilities is what mathematicians refer to as casework. We're considering the different possible cases of n. Is it a positive integer? Is it a negative integer? What else could potentially be happening, right? I think here there's even a third case that you could say, where what if like n happens to be nothing, right? If n is zero, then the negative version of that is zero, and then you might even say that neither of them is greater than the other, right? In that particular instance. So we're kind of practicing like this skill of logical thinking, like what are all the possibilities of the original statement? And then in each one of those, what are the consequences, right? As we move to test the right-hand side of the problem. So you might notice that some of these have like a definite correct answer, and some of them might have like kind of a dependent answer that sort of depends on how you're thinking about the setup of the problem. And I want you to sort of discuss those as you go with your table partner, right? Very much so, you might notice that there's several answers to some of these problems, and it all sort of depends on the start of the scenario. So as we go, I want you to maybe pause the video and take maybe, I don't know, 15 or so minutes to give it a go with the rest of those remaining statements, and we'll kind of pick up and go from there. As you work, I'll sort of work it out myself here and arrive at my own conclusions about what's potentially happening with each of these. But like I said, I want you to pause the video here and try it yourself, and then bring it back after like 10 to 15 minutes. We'll sort of discuss and take it there as a full group. All right. So after you guys have kind of worked ahead a little bit and sort of got up to your elbows, like playing around with some of these and like testing and considering some of these different cases, I want to work through maybe a handful of them, kind of point the way with what we're going to see here for some of these expressions and over which one is ultimately greater than the other. Now, in our first statement, they tell us that some unknown number x is greater than some other unknown number y. We don't know hardly anything about X or Y. I don't know if they're both positive, if they're both negative, if one's positive or one's negative. So what I might do here is kind of consider like all possibilities on the number line, right? I might engage in some casework. Let's say that they're both positive numbers. Let's say that X is greater than Y, but Y is like a small positive number and X is a big positive number. If I think about adding or subtracting some value for A onto these guys. What I want to think about is what that's going to look like on the number line, right? So let's say that I want to add A to Y and onto X at the same time. Well, if they're both positive numbers, then that's going to mean both of these guys shift further right on the number line, but X plus A is still greater than Y plus A. So in that case, that definitely seems to be telling us that X plus A is greater. But let's maybe consider a different case. Let's consider maybe a case where they're both negative. Now, x needs to be greater than y, so it needs to be closer to 0 than y is, but they're both off to the left, right? And let's say that I'm adding a to both of them to kind of move them the same distance to the right to get a new value. Well, I'll see there that in both cases, y plus a is less than x plus a, so x plus a is greater in that case too. If I think about maybe the third possibility where one of them is positive and like one of them is negative, if I know that x is greater than y, then I might say that x is to the right of 0 on the number line, and y is off to the left. Y is a negative, and x is a positive. Even here, if I think about like adding a to both of these expressions, what I'm going to notice is that x plus a is greater than y plus a. So in all three of those different setups, I see that the same fact is true. That when I add a to both sides of the inequality, I'm still preserving the initial truth value, right? Just like we saw in our warm-up. You'll see the same thing with x minus a or y minus a. There's three different cases that you might explore where x and y are both positive, or they're both negative, or x is positive and y is negative. It's just that instead of shifting them to the right by adding a in the number line, you're actually shifting them off to the left by subtracting by a on the number line. So regardless of your setup, what you're going to notice there is that if you're shifting up or down by adding or subtracting by a certain number, you'll still see that x minus a is greater than y minus a. There's no difference there, right? Now, let's maybe start with different setup. Let's say that we have actual concrete numbers, right? 5 is greater than 4. So on my real number line, I might mark out 4 and 5, but then I'm introducing something new, right? Which is greater, 5 times x or 4 times x. Now, I've got to consider some of the possibilities for x, right? If x is a positive number, like say 3, what I'm going to notice is that 5 times 3 is 15, right? And 4 times 3 is 12. That would be kind of like saying that we're taking 4 and we're moving it to the right the same distance, like x times in a row. But we do the same thing with 5, right? We're moving it the same distance off to the side, x times in a row. So we'll see that when x is a positive number, 5 times x is greater than 4 times x. When I multiply both sides of the inequality by x, it didn't change the truth value. But what if x happened to be a negative number? What if, say, x was like negative 2? Well, if I did 5 times negative 2, I'd get something like negative 10. And if I did 5 times, or rather 4 times, I think I messed this up here. Let me start this over. If x is negative 2, right? And I do say like 5 times negative 2, there we go. That is negative 10. And if I do 4 times negative 2, I get a value like negative 8. So as I take a look at my number line here, and I'm thinking about like different possibilities or cases, if I've got, say, 4 and 5, and I move them like left a certain number of groupings of steps, I kind of actually get the opposite being true, right? I would see that 4 times x, when x is negative, is actually greater than 5 times x. So depending on which one you're going with, if you're saying x is positive or x is negative, you might actually say that one or the other is greater. There's also kind of like a third possibility here, right? What if you said x was equal to 0? Well, if x was equal to 0, then 5 times 0 would be 0, and 4 times 0 would be 0. So you'd go and compare 0 to 0, and you wouldn't say that one's greater than the other, right? They're actually equal. So problem 3 is kind of the first place where we run into an interesting problem, right? So long as I'm multiplying by a positive number, I maintain the original truth value and I don't have to change anything around, right? But if I multiply by a negative number, I'm going to have a problem. I have to switch the original inequality. So instead of greater than, I'd have to switch it to kind of like less than, right? It gets a little more interesting with problem 3. Now, let's go forward and say that we want to investigate like 5 greater than 4 in the setup. Well, what if we're dividing by x, right? You'll see something really similar here. If you think about division by a number, if I've got like 5 divided by, say, I don't know, x equals 2, right? Let's say we're dealing with a positive number. Then 5 divided by 2 would give me 2.5. 4 divided by 2 would get me 2. It would definitely appear that 5 divided by x is greater than 4 divided by x. But it's not necessarily guaranteed to always run that way, right? What if x was like negative 1? Well, if I do 5 divided by negative 1, I get negative 5. If I do 4 divided by negative 1, I get negative 4, and negative 4 is greater than negative 5. So the original inequality doesn't work anymore, right? So depending on the value, you see a similar problem here. If I'm multiplying or dividing by a negative number, I've got to think about the inequality backwards. I've got to switch it the other way around, right? So 3 and 4 are kind of highlighting this multiplicative or divisive property of inequalities, that if you multiply or divide by a positive number, nothing changes. But if you multiply and divide by a negative, things are very different, right? If you chose x equals 0, you notice that you get undefined results because we don't know really what it means to take something and divide it into no groups. You can't really choose x equals 0 in this context compared to like what you saw with multiplication. Now, let's say that we move on to statement 5, that y is less than x. We're trying to figure out which is greater, x minus y or y minus x. Now, again, there's kind of some casework that can be done here. If we assume that both of these are positive numbers, but x is a larger positive number than y, then x minus y would yield a positive number. Y minus x, on the other hand, though, would yield a negative number. If I had like 3 minus 4, that's negative 1, versus 4 minus 3 is positive 1, right? So it would turn out that x minus y is the larger value than y minus x. But what if they're both negative? Let's say that instead of both being positive, I got x is a little closer to 0 than y. If I do say like x is negative 2 and y is like negative 4 as an example, right? Then negative 2 minus negative 4 is going to look like positive 2. And if I do it the other way around, where I do negative 4 minus negative 2, that's also going to look like negative 2, right? And 2 is greater than negative 2. So x minus y still turns out to be larger than y minus x. Now, as a last case, let's see what happens if, say, one's positive and one's negative. Now, remember that x is greater than y, so x might be the positive number and y might be the negative number. If I choose x to be like 4 and y to be like negative 2, what I'm going to notice here numerically is I actually run the calculation is that 4 minus negative 2 is 6. Negative 2 minus 4 is negative 6. So in all three cases, x minus y turns out to be the larger quantity. And that goes back to what we saw with part 1 and 2, right? There were those three same cases that we were working with where we're adding a constant versus like subtracting or adding two variables together. But it's the same property, right? If you add or subtract on both sides of the inequality, you preserve the initial truth value of it. It doesn't make any difference whether you're dealing with positives, negatives, or the mixture of them. Now, with part 6, we kind of graduate up to a more challenging scenario, right? Here, I've got the expression 2x minus 3 is greater than 7, and they want us to make a determination about whether 5 or x is greater. But we don't know what x is, right? So we should probably figure out what value x is going to hold in this, and this might be the first time that we're going to solve an inequality in order to try and make this determination, right? So what I know so far is that in addition and subtraction, so long as I do the same thing to both sides, I preserve the truth value of the initial setup, right? So if I see like a minus 3 on this left-hand side of the inequality that I want to undo or I want to solve, I can add 3 to cancel it, but in order to preserve the truth value, I've got to do it to the other side as well, right? That's the same for what we did with equations in the context here of an inequality, so it's no different, right? That setup is still going to hold. So that would tell me that 2 times x needs to be greater than 10. And if I wanted to keep going and solve for the value of x and what it needs to be greater than, my next thought is, well, maybe I got to do the opposite of multiplying by 2. I've got to divide by 2. Now, I've got to be careful here, right? Because we saw some examples in the past where if you're multiplying or dividing by a negative, things aren't the same, right? You kind of have to switch the inequality the other way around. Given that this is a positive number, I don't have to worry about that. So I can say here very directly that x is still greater than. It's just now on the right-hand side that it's greater than 5. So if this is true, then that would tell me that x is the larger quantity. X is greater than 5, even though I don't know what it is, right? And I may never will. So that is how we kind of move from solving equations into the work with solving inequalities. The first kind of like 5 or 6 examples, we're focusing on like the initial properties, right? What's fair game with addition, subtraction, multiplication, and division. Now where we're going is we're saying, okay, how do we use it to actually do some work and solve? And you'll see a lot more of that here as we hit the kind of last chunk of these examples. Now, let's say that I've got 10 minus 2x is less than 6. I want to try and figure out which is greater, x or 2. If I think about 10 minus 2x being less than 6, I know to solve that first on this x, I multiplied by negative 2 and then I added 10. So that means to undo this, I'm going to take away 10 from both sides. Now, I can do that and preserve the balance of the inequality. One thing that I want to think about is whether adding or subtracting something needs me to flip the inequality the other way around, right? Whether it's still true. And we saw from earlier examples that this is totally fine, right? There's no problem with this. So now I'll see that negative 2x is less than negative 4, right? Now, to undo the negative 2 times the x, I'm going to divide both sides by negative 2, and here's where I've got to be careful, right? If I divide or multiply by a positive number, there's no problem. But if I multiply or divide by a negative, I've got to be really careful here, and I've got to switch the inequality because the opposite is going to be true. So negative 2 divided by negative 2, that cancels on the side with x. If I do negative 4 divided by negative 2, that switches to positive 2. But my final step here is now I've got to switch the inequality the other way around. And I see here that x is greater than 2 strictly. So it's very much the larger of those two quantities. Really tricky, right? When we're multiplying or dividing by negatives, we got to be super careful about maintaining the truth of the inequality, which means that we need to flip it. So we'll carry on from there with, say, statement 8, that 4x is less than or equal to 0, right? If I want to get the x by itself and determine whether x or 1 is greater, then what I can do is divide both sides by 4. When I'm multiplying or dividing, I've got to be careful. In the context here, if I'm dividing by a positive number, I can keep the original inequality, right? I don't have to switch it. If I take nothing and I split it up equally into 4 groups, I've still got nothing. So what I'm going to see here is that x is less than or equal to 0. So if I'm trying to figure out like which of these is greater, right? Well, x could be nothing, which is definitely less than 1, or it could be a negative number, right? It could be less than 0, which is still less than 1. So in both cases, 1 is the greater quantity. Now, part 9 gets kind of interesting in the sense that they tell us x is a positive number. It's greater than 0, but it's less than 10. And they then tell us that y is a positive number because it's greater than 0, but it's also less than 12. And they want us to determine which is greater. Is it x or is it y, right? Now, the thing that's kind of interesting here is that there's a whole bunch of different things that x and y can be. They can be any number that's greater than 0, but x can only be up to 10, not including it, and y can be up to 12, but not including it. You'll notice here that I've drawn some real number line graphs, where in red, I'm saying like these are all the possibilities, right? But I've used these open circles on 0 and 10 to say that those are out of the question, right? I can't quite use those because I don't see less than or equal to in these pairs of inequalities, right? So it kind of depends here. One thing that could happen is maybe I say, okay, well, let's let y equal 11 and let's let x equal 9, right? If I think about what's happening here, then I would definitely say that y is greater than x. There's no problem, right? But is it possible that you choose like a different setup where this isn't true? Think about this. What if x is equal to 6 and y is equal to 2? Well, then it turns out that x is greater than y. So depending on how you're setting this up, you might notice that there's not really an answer, right? And sometimes with inequalities, we just don't have enough information to make that determination. Depending on some of your choices, you might see that one thing is true or the other. You might even say that in most cases, right? Maybe y is greater than x, but there's like a very small collection of cases because y could be like 11 or like 11.5 or like 10.9, in which it's definitely greater than x. It's hard to make a determination though and say really which one it is. So sometimes with these inequalities, there's just not enough information to figure out the answer. Now, this last one here, this exponential statement, right? 3 to the n plus 2. We say whatever that is, it's greater than 27. We're trying to figure out which is greater, this mysterious number n or the number 1. Now, one thing that I want to point out here is that 27 could be broken down as like 3 times itself a certain number of times. And this goes way back, right? To I think some of the work we were doing in Unit 1 and Unit 2 in August and September. I'm going to think about like a prime factorization of 24, or 27 rather, and build out a factor tree to see like how many times 3 times itself is going to go into 27. If I think about like 3 times what equals 27, I'm going to see it's like 3 times 9. But then notice for 9, I could say that that's like 3 times 3. So one way that I can think of 27 is the number 3 to the third. So we're saying that 3 to the n plus 2 must be greater than or equal to 3 to the third. Now, if this is true, the 3's don't really matter anymore, right? I'm more focusing on the exponents to say, okay, well, then that must mean n plus 2 is greater than the power 3. And if this is true, that means I can kind of take away 2 from both sides of the inequality and not really harm anything, right? I'm maintaining a balance. And with adding or subtracting, it doesn't matter if it's positive or if it's negative. So this is going to tell me that n is greater than or equal to 1. So if I'm thinking about whether n is greater than 1, I suppose it could be, right? That's part of our inequality. But it could also be equal to 1. So if I was asked strictly, like which one is larger, there's maybe the possibility that it's actually not larger, it's the same. So it's also kind of an undetermined answer here, right? We're not really certain which it could be. I would say like at a minimum, these things are equal. Maybe in most cases for n, it could be larger than 1, but I'm not certain, right? I need just a little more information about the setup to really make that call. But I want you to think about here, like the logic, right, of how we're making these determinations. We're considering all the possible cases. We're trying to figure out what's happening on both sides of an inequality. And we sort of started this activity by thinking about like what's fair game in terms of operations, right? Can I add and subtract? Can I multiply and divide? Does the truth value change? Does it stay the same? Once we build off of those initial properties, these last few statements, we're actually doing algebra and solving inequalities fully, right? So that's kind of the big takeaway for our time for today, that there's like a logical way to work with these inequalities that's fair in the sense that we're balancing kind of like equations, but there's like specific properties we got to keep an eye on, right? Adding or subtracting on both sides, multiplying or dividing. Here's maybe one last one to kind of get the gears turning again. Let's consider, say, a statement that A is greater than 0, but B is less than 0. Which one's greater? A, B, or A divided by B? Try this one on for size real quick and see where you get. All right, so as we wrap it up, right, we kind of solidify our understanding and get ready to move into like our work time. We have this initial statement that A is some mysterious number greater than 0. B is some mysterious number that's less than 0. So B is negative and A is positive. If I'm trying to figure out like which one's greater compared to say like A times B or A divided by B, some interesting possibilities might be popping up in the process, right? If I think about what AB is going to look like, it's a positive number times a negative number, which means overall it's going to look like some kind of negative result, right? Even if I don't know what its value is. If you think about A divided by B, then you're doing a positive number divided by a negative number, which is also going to turn out to be a negative result, right? So they're both negative numbers, which doesn't really help me determine right off the bat, like which one's greater than the other. So now we're kind of thinking, okay, how do I go further, right? And one thing that we might consider is like the potential for some different casework. So let's maybe try a different setup. Let's say like A is equal to 5 and B is like equal to -2. just for giggles, right? Just to pick some finite values and see what happens. Well, that's going to tell me then that a times b is negative 10, but a divided by b is like negative 5 halves, which is the number negative 2.5. In that particular case, I'm going to see that a over b is greater than a times b, because negative 2.5 is closer to 0 than negative 10. Let's maybe try a different case, though, where we say like a is equal to 1 and b is like negative 4, and see what happens, right? I'm just sort of testing some random choices of numbers, right? I'm just sort of playing around and seeing what happens. From here, if I choose these as my cases, then a times b, 1 times negative 4, is going to look like negative 4. If I do a divided by b, well, then 1 divided by negative 4 is negative a fourth, which is the same thing as negative 0.25. And in that case, a divided by b is still greater than ab. If I'm thinking about like what's happening here, right? And I'm thinking maybe a little more algebraically instead of choosing cases with some numbers and values. There might be like a particular case I could choose where I actually see that one is not necessarily greater than the other, right? What happens if I choose like A is 1 and B is negative 1, for example? So that's also like a possible thing to consider. But what I want to think about here, right, is what if we say A over B is greater than BA? Well, if I wanted to say undo this, right, on both sides of the inequality, I could multiply both sides by b, but be careful, what kind of number is b? It's negative, right? So if I'm playing around and just sort of rewriting this, I'd have to be careful to switch the inequality. And what that would then tell me is that a is less than like ab squared. I don't necessarily know that that tells me a lot of interesting information, right? If b is a negative number and I square it, it goes back to being positive. So I have a positive times a positive is less than just a regular old positive number. But it's maybe something I can do to just sort of play, right? Just to sort of mess around and see what happens. So in that kind of instance, I might see that this is true. Maybe that kind of leads me down a rabbit hole where I'm sort of playing around and I might discover something. It strikes me that in most cases, A over B is greater than AB. There is a case I can imagine where A is like positive 1 and B is like negative 1, where I see that there's really no difference here, right? If I see like AB, then that's times each other, that's negative 1. And if I do A over B, that's also negative 1. So I'd actually see that AB is equivalent to A over B. So I couldn't necessarily say in all cases that A over B is always greater than AB, right? I might be able to say that like A over B is either greater than or equal to AB. That would be fair, right? But I couldn't say that it's strictly greater, right? So I would say that overall this problem may not have a solution. But it's nice to kind of play with, right? The goal here is not necessarily to arrive at a definite answer so much as it's to consider those different possibilities and think through their consequences, right? That's the casework side of mathematics. And that's how we solve mathematical problems. And that's how ultimately we lead off into like making discoveries and combinations in math with other methods. So to kind of bring it all back together, the big takeaways for working with inequalities that I want you guys to track is that if you have an initial inequality, like say x is greater than y, there are two properties that you can always do where you don't have to worry about changing the sign, whether it's facing one way or the other, because the truth value is the same. And that's the addition and the subtraction property. If you start with the original inequality that x is greater than y, you'll see that x plus a is always greater than y plus a. And the same thing is true for x minus a being greater than y minus a. The multiplication and division property is a little more complicated. In the multiplication and division property, if you start with that initial setup that x is greater than y, and you multiply or divide both sides by a, so long as it's a positive number, you still have the same original truth value. So you don't need to flip the inequality. But it's different if a turns out to be a negative number. If you multiply or divide both sides of the inequality to maintain the balance, which is good, by a negative number, you're going to have to do the opposite truth value of what you started with. So for example, if x is greater than y and I multiply both sides by a negative, I'm going to see that ax is now less than ay. And similarly with division, if x is greater than y and I divide by a negative number, I'm going to see x divided by a is actually now less than y divided by a. Kind of a tricky section, right? There's one last thing with the multiplication property that we saw a little bit in our work. If you start with like x is greater than y and you multiply both sides by 0, you're not really dealing with an inequality anymore, right? Because you'll have nothing is actually equal to nothing. It's not greater than or less than itself. It kind of switches back to an equation. These properties exist across the board anytime there's inequalities at play. Once you know that these properties exist, like we saw in the last part of the activity, you can actually start solving algebraically for a value for x. Like we see in part like 6, 7, and 8, once you have like an expression, you can sort of use inverse operations on both sides of the inequality. You can figure out like a range of values that x might take. And that's ultimately the direction that we're moving in as we get into our ready, set, go for today and into the rest of our unit. So today we're kind of focusing on the logic of it, right? How do we test these different cases? How do we know that things are still true? When are they going to be different? Now that we have those properties, we kind of graduated up into solving not just equations, but also inequalities. So going into the rest of our time for today, what I want you guys to work on is the Ready, Set, Go for lesson 4.4. I'm hoping that I'm going to be back on Friday and feeling much better. When we come back on Friday, we'll kind of recap and review, and I should have for you guys ready to go the graded versions of the summatives that you took from our time in class on Monday. Otherwise, though, I hope you guys have a fantastic rest of your day. I will see you guys soon. Take care.